Oke, terima kasih. Oke, thank you very much. So, back to our webinar. So, maybe I will give this time to Dr. Fajar. Please,
Okay,
Fajar Setiawan.
thank
And I'm
you.
sorry, maybe I cannot follow until finish because I'm in field survey. So, good luck and enjoy this webinar. Thank you very much. Silakan Pak Fajar.
Okay. Uh, Thank you, Dr. Luki, Head of the Research Center for Limnology and Water Resources BRIN. Assalamualaikum warahmatullahi wabarakatuh. Good morning and greeting to all speaker and participants, Mailisu Phd and also Dr. Novi Susetyo Adi. My name is Fajar Setiawan and I will be your moderator today. Webinar titled Application of Earth Observation Data for Sustainable Water Management. This webinar is organized with the support of the Research Center for Limnology and Water Resources BRIN, the Indonesian Society for Limnology-MLI, and the Indonesia Ocean Color Community. Today, we are honored to have two distinguished speakers. First is Ms. Mailisu, PhD candidate from the Faculty of Life and Environmental Science, University of Tsukuba, Japan, who will present on estimation of suspended particulate matter concentration in various water bodies. Mailisu is already here. And the second speaker is Pak Novi Susetyo Adi, PhD, Head of the Marine and Fishery Socio-Economic Research Center, Ministry of Marine and Fishery Affairs. He is a member of the Indonesian Superior and Mapping Association, Satu Pasti, who will present on ocean color from science to application to support decision making in marine and coastal environmental management. Okay, before we begin, I would like to introduce the first speaker. Is Mailisu Phd. I will share my this curriculum vitae from the Mailisu Phd. Everyone can see my screen. So Mailisu is the PhD candidate of the University of Tsukuba, Japan. His education background is she obtained the bachelor degree from the University of Shandong Agricultural University, China. She obtained her master degree in environmental sciences, University of Tsukuba, Japan, with the concentration of study is remote sensing application in arid ecosystem assessment and vegetation diversity evaluation. Currently, he is pursuing a doctoral degree with the main research is estimation of inherent optical properties of water body by integrating machine learning and also quasi-analytical algorithm or QAA using remote sensing to estimate suspended particulate matter concentration. Good morning, 𝐏𝐞𝐦𝐬, Mailisu-san. You already here and ready to present your research, right?
Yeah, can you hear my voice?
Yeah, we can hear your voice clearly.
Okay, I will share my slide.
Okay, please, your screen is yours.
Okay, wait a moment.
Okay.
Uh, so if you can you see my slide?
Yes, everything is good. Please go ahead.
Okay, thank you. And good morning, everyone. First, I would like to thank Dr. Fajar for inviting me to give this presentation. And my name is Mailisu, and I'm from China. And for now, I'm a PhD candidate at the University of Tsukuba in Japan. I belong to the Matsushita Research Group. The group research work mainly focus on the water quality monitoring of various water bodies using the satellite remote sensing and the bioptical models and the integration of remote sensing with ecosystem studies, degradation, and sustained measurement of inland waters, and also about the development of machine learning and deep learning approaches for improving the geographic object segmentation and access of urban surface such as rooftops and impermeable areas. And my own research focused on the remotely estimating the suspended particulate matter concentration and the inherent optical properties. And today I will be presenting my latest research findings. If you are interested in similar research topic, I would be very happy to exchange ideas and explore the potential collaborations. And today my topic is about introduce a method to remotely estimate the suspended particulate matter concentration in various water bodies. And for the research background, and the suspended particulate matters, we call it the SPM in short, are the first particle of sedimental in the water. It is one of the important water constituents that determines the water clarity. Look at the left finger. The water is murky due to a high concentration of SPM, leading to high turbidity. So the light cannot reach the deeper layers, provided the plant growth and distributing the aquatic ecosystems. And when the particles are stirred up, carried by the current, and eventually set down, the SPM show us the balance between the erosion and the deposition. And SPM consists of the particles such as soil, sedimentals, and organic matters. It means it can control how these materials move and where they end up. Therefore, the knowledge of SPM is essential to understand the Earth system process and address the challenges related to the water resources, ecosystem, and even the human health. And to obtain the SPM, the traditional field measurement of SPM are reliable, but they have clear limitations. They usually provide only limited spatial and temporal coverage, since the water samples are taken at the specific location and times, and they are also time-consuming and costly. And the satellite remote sensing offers much broader coverage. It allows us to monitor the large areas repeatedly and efficiently, and even provide access to historical data, even the 10 years or 20 years. However, the remote sensing also has challenges such as the need for proper algorithm to convert the satellite signals into the accurate SPM values. So the concentration of the SPM, which represents sum of two optical active substances, like the phytoplankton and the non-algal particles, which can be estimated from the remote sensing reflectance or water-leaving reflectance. So, developing a mathematical model that describes the relationship between the remote sensing reflectance spectrum and SPM is very important. So when estimating the SPM using the empirical, when estimating the SPM remote sensing, two main approaches are commonly used. One is an empirical algorithm, then the other is semi-analytical algorithm. The empirical algorithm have the advantage of being simple to apply. However, they also have the clear limitation. They always require the in situ data for collaboration, which make them highly dependent on field measurement. And on the other hand, the semi-allocated algorithm are based on the visibility theory, which makes them more physically grounded. They do not require frequent recalibration, and their transferability is higher. So once developed, they can be applied to different water bodies with good reliability and broad applicable. So they can be as a nice algorithm for the global water parameter search. So for some background about semi-allocated algorithm, for any water bodies, the SMEM can be estimated from the ratio of the particulate backscattering coefficient, we call it the BBP, to the specific particle backscattering coefficient, we call it BBP star, as the reference band. The key offshore properties used in this estimation are the obtained the algorithm to coefficient. The BBP, the particle backscattering coefficient are commonly retrieved from the remote sensing reflectance using the one model we call it the 𝐏𝐸𝐬𝐭 algorithm, the QAA. And the different version of QA models have been developed, and the obtained for various water bodies, like the original version of QA for clear waters, and they have a 𝐏𝐸𝐬𝐵6 for the turbid waters. So in our research group, the Dr. Jiang proposed a semi-allocated method for estimate SPM in clear to extremely turbid water. In his study, the world water are classified into 4 types. According to their turbidity levels, then appropriate reference wavelength was selected, and the original quasi-allocated algorithms or its modified version was applied to estimate the BBP for each water type. And finally, the obtained the BBP will converted to SPM concentration for each water type using the fixed specific particle backscattering coefficient, the BBP star. However, this study using the fixed BBP star will based on one assumption that the BBP will depend only on the SPM concentration. However, for recently, this assumption does not necessarily hold true, as the natural water typic exhibits have a variety of particle compositions. So, no matter the empirical or the semi-allocated algorithm, both algorithms encountered the 2 major issues when applied to water bodies with a wide range of SPM concentration. First, the RRS saturated in water with a high SPM concentration at a shorter wavelength, like the green or red band. So the RRS at the longer wavelengths must be used to estimate SPM in such waters. So to address these challenges, the 𝐥𝐤𝐭 and some studies have developed a multiplied SPM estimation algorithm along with the optical water type classification schemes, we call it OWT, to accommodate the different water bodies. And the second issue is due to the differences in refractive index between the organic and mineral dominated water, and the variation in particle size, shape, and the density in natural environment. The remote sensing reflectance of water body is not determined solely by the optically active substance concentration in the water body. So based on this theory, the assumption about the BBP values in 𝐥21 does not hold true. So we need to find or establish a water type classification scheme that relies on the particle composition of the water bodies. So this is a research objective in this study. To solve these problems in current study, the objectives of this study is first to propose a new water type classification algorithm which can be considered both of turbidity and the particle composition of water body, and the particle develop a series of sub-algorithms for SPM calculation to estimate the more accurate SPM concentration for each water type defined in this study, and then evaluate the performance of the new algorithm. And this is data. We used a comprehensive in-situ data set was collected from a data set called the Gloria dataset. And there are about 4,000 remote sensing reflectance and SPM data pairs it's not a remote sensing reflectance, it's just reflectance and SPM data pairs from 394 water bodies globally. And we used SPM values range from about 0.09 to 2,000 grams per cubic meters, and with half of them below the 10. And the developed algorithm was also evaluated using the real satellite image data. For this proposal, two matchup data sets were collected. The first one is taken from the Gloria dataset and the corresponding Marist satellite data. And another one is obtained from 𝐥𝐤𝐬𝐿21. A total of 226 matchups were used to evaluate the new algorithm. And about the method. So this is the optical water type based algorithm for estimating the BBP. This OWT-based water type classification proposed by 𝐥𝐤𝐬21, I just mentioned in background. In this study, this method was adopted in this study to enable the semi-allocated estimation of BBP across the diverse water bodies. This table shows how to estimate the BBP from the remote sensing reflectance one by one. Compared with the previous study, 𝐥𝐤𝐬21 added the stamp of the optical water type classification. The worst water are classified into 4 types according to the turbidity level. This classification scheme is used to determine the most appropriate reference wavelength. That means the fundamental requirement of the QAA model corresponding to each water type. In details, the QAV5 is used for clear waters, and V6 for moderately turbid water, and the QA turbid for highly turbid water and extremely turbid water. Then the corresponding empirical equation are used to estimate the ANW coefficient and the non-water absorption coefficient and the total absorption coefficient. Finally, the BBP values for each types can be obtained. And for the selection of appropriate BBP star based on one particle composition classification. So unlike the BBP values, there is no effective method yet to estimate the BBP from the remote sensing reflectance. But previous studies have reported that the value of BBP is strongly correlated with the particle composition. For example, the organic dominated water generally have the low BBP values and the BBP star values, and the mixed mineral dominated water have higher values, and the mixed water have the intermediate BBP values, BBP star values. So therefore, the use of dynamic BBP values instead of fixed BBP values may improve the accuracy of SPM estimation in global water. So how to classify the water bodies with the different particle composition based on the remote sensing reflectance. Their previous study have shown that we can use the one ratio, the ratio of particled organic carbon, the POC, to SPM. So which can be, it can be empirically estimated from the remote sensing reflectance and has been used to identify this ratio can be used to identify the particle composition of water bodies. So in this study, the empirical formula of green band recommended by 10-21-25 was adapted to estimate its POC divided SPM. Also, we proposed a new particle composition classification scheme for by combining the threshold recombinant in 3 studies. That is a POC, the ratio of POC and CPM larger than 0.12 for organic dominant waters, and the POC, the ratio of POC and SPM smaller than the 0.06 for mineral dominant waters, and the wheel in the middle we call is mixed water taps. So after the particle composition classification, for different particle water types, we select the corresponding BBP star wheel. The wheels obtained from Zone 21, as we mentioned earlier, the organic dominant water types have the lower BBP star wheels, so we use the blue line to ask the BBP star wheels of the organic waters, and the higher wheel for the mineral dominant waters, and the medium wheels we used for the mixed water types. And using the above 2 water type classification schemes, the optical water type classification and particle composition classification, the water body around the world can be classified into the 12 water types, because there are 4 types for the optical water type and 3 types of the particle composition type. And we developed the 12 water types basic SPM estimation algorithm. Like for example, if we input water remote sensing reflectance, this water pixels is classified as organic water dominant water type, and also for the highly turbid water types. The third SPM estimation formula is selected to be estimated the final parameters SPM. So to validate the accuracy of our algorithm, we also compared it with the other 11 SPM methods, include 3 empirical algorithms using the multiple equations based on the different optical water type classification, and 1 empirical algorithm based on the each water type classification, and the semi-analytical algorithm based on the water type classification, the Zone 21. Also, we compared the 1025. So this is about the result. This is the remote sensing reflectance of 12 water types identified in this study. Of the 12 defined water types, 10 will find in the Insuta dataset, the 𝐥𝐤𝐬 dataset. The rows indicate the different optical water types, and the columns represent each particle composition water types. Like the fingers in the first row is classified as the clear water in the optical water type classification, and which filter contains organic, mixed, and mineral water bodies in particle composition. And this slide is the remote sensing reflection with highly turbid and extremely turbid water types. The remote sensing reflectance with the highest proportion in 𝐥𝐤𝐬 datasets correspond to the water bodies with a high concentration of mineral particles in highly turbid waters. So from those 12 fingers, we can see that the remote sensing reflectance belonging to the same optical water type may have the different particle composition. You can see the fingers in the same row, and the remote sensing reflectance with similar particle composition may be classified into the different optical water types. You can see the fingers in the same columns. In general, the remote sensing spectral shape varies depending on the optical water type classification, and the magnitude of remote sensing reflectance strongly depend on the particle composition classification. We can also see it from the mean spectral across the 10 types. The green, yellow, and pink colors means the mineral, mixed, and organic water type. And in each color, the shape of the point means that the different optical water types, like the circle point means that the clear water type, and the triangle means the highly turbid water type. You can see the magnitude of the remote sensing reflectance strongly depend on the particle composition classification. Usually, the mineral dominant water type is greater than the mixed, and which is greater than the organic dominant water type. And this is the box plot of SPM distribution for the 10 detected water types in Susetyo data. It shows that several water types with different optical water type, as well as the different particle composition, can have the similar SPM values. This result indicates that it is very difficult to select the optimal SPM estimation algorithm based only one water type classification scheme, because one water type classification it means they use the same reference band, and as I mentioned in early, those spectrals are very different. So how those reference band can be estimated the different SPM values. So in other words, combining to the two water type classification scheme could improve the accuracy of SPM estimation. So this is the in Susetyo dataset result that 3 empirical algorithms that use only one equation. The x-axis is the in Susetyo SPM, and the y-axis is the estimated SPM. You can see all 3 algorithms difficulty dealing with the SPM estimation over a wide range. It show a large overestimation at lower values, or the large underestimation at high SPM, or overestimation at the high SPM values. So for the metrics of the accuracy, especially for the MDAPE, the median absolute percentage error, this will, if the higher this will, it means the lower predictive performance. So the values for these 3 methods are all above 50%. But this issue can be mitigated by switching between the multiplied equation based on the water type classification. So this result by selecting this is empirical algorithm using the multiplied equation based on the optical water type classification. So by selecting the more appropriate equation for each optical water types, it can significantly improve the SPM estimation accuracy at both low and high SPM concentration. You can see that each color represents one water type, and each water type uses a different estimation formulation of SPM. However, the topical limitation of empirical algorithm also showed in the 2 graph. Their performance is highly dependent on the collaboration data used. The method of 𝐥𝐢𝐬𝐿17 and the NOVA17 used the similar optical water type classification method. You can see the color is is almost same, but those 2 methods were calibrated use the different data set, and therefore the performance differently on the in Susetyo data set. you can see the purple point of the data. For those data with high SPM concentrations. And this is another 3 empirical algorithm based on the water type classification. From the R-circled and MDAP, these 3 algorithms are better than the previous 3 algorithms. It might be because the more appropriate optical water type classification you used, and the classification data cover a broad range of SPM concentration, the accuracy can be improved. This is an empirical algorithm based on the water type classification. The 𝐸25 is based on the we call it the particle composition classification, and the 𝐥𝐤21 is based on the optical water type classification. The 𝐸25, you can see the 𝐸25's result. The empirical formula limitation can be mitigated by using the semi-alkyl methods. The 𝐥𝐤21 and our methods are all semi-alkyl methods. The fingers from left to right is 𝐸21 and 𝐥𝐤21, and our studies. The classification and our algorithm based on the 2 classification methods. So you can see that the 2 semi-algorithms show better applicability across the entire data set compared to all the empirical algorithms. The newly developed algorithm in this study showed that the best performance in SPM estimation with the smallest MDAP and the second smallest RMC, and the slope is closely to 1, and the R-circle is the second highest. So which indicate that the new algorithm can better capture the real SPM variation compared to other existing algorithms. So in our study, each improvement obtained by the 2 classification method, what we wished to show other researchers. So to investigate how water type classification can add in SPM estimation, we compared the 3 methods for each particle composition water type we defined. The figure showed that the organic dominant water type samples, which defined by our study, the color of the dot in all 3 fingers means the optical water types defined in 𝐥𝐤21, and the mark represent the particle composition based water types in first finger are defined in 𝐸25. The classification definition is a little different. So the 𝐸25's classification result is different with our studies. So although the 𝐸25 not use optical water classification, for easy to compare, we have also displayed the corresponding optical classification colors for his data points. So the result shows that the 𝐸25 has a significant underestimation. In this part, the result which is significantly improved by our studies. The MDAP and RMSE also decreased. So compared with 𝐥𝐤21, although the MDAP is slightly larger, about 0.2%, but our methods reduces RMSE and improves the bias. And for mixed water types, our method also improved the SPM estimation compared to 25, reducing the MDAP from the 46.1% to 36.6%. And I need to mention that our method estimation uses the 3 different algorithms. And it means use the 3 different bands and 3 different equations based on the optical water type classification. In mixed types, the 𝐸25 uses the same single empirical algorithm for most water samples. You can see they have 300 data belong to the organic rich type, and in contrast, our method using the 3 different algorithms based on the optical water type classification. So our method shows significant improvement for most error metrics. And because 𝐥𝐤21 uses the same BBP star view. The median views is like our result of mixed water tap. So the result is the same. And for the mineral dominated water defined in this study, our method outperformed both 1025 and 𝐥𝐤𝐭 with the lowest MDAP and RMSE views because we combined the advantage of two water type classification schemes. And we assess the performance of new SPM algorithms with the real satellite images, the matchup data. Among the axis is in suited SPM and the y-axis the estimated SPM views. So among the 226 matchups, there were 9 water types well detected, and the accuracy of SPM using our method from the real MARIST and OLCI satellite data was similar to the estimate from the in-situ remote sensing reflectance with an MDAP of 43.4%. And to verify the capability of the newly proposed algorithm in our study, we applied to real satellite images and present spectral distribution of optical water type and particle composition water type and the SPM in 4 lakes. And you can see that the spatial distribution pattern of the particle composition map, the third column, is different from that optical water type classification maps. Most of water pixels in Lake 𝐏𝐈𝐻𝐬 of Japan and the Lake 𝐡𝐭𝐭𝐩𝐬 of Kenya belong to the green color, which is the mineral dominated water. However, in terms of water turbidity, the optical water type, the water pixels of Lake 𝐏𝐈𝐻𝐬 were classified into 2 water types: the highly turbid water type, the yellow color, and the extremely turbid water type, the red color. And the water pixels of lower Lake 𝐡𝐭𝐭𝐲 were classified into 3 water types: the mandatory turbid type water, the blue one, and highly turbid water and extremely turbid water. This means the 2 optical water types represents the totally different information of water. And this is a showcase of the lake area of the North America and the Lake 𝐏𝐤𝐻𝐬. And also we show the showcase of 3 estuaries. In all 3 river estuaries, the Mandan River, Nilo River, and Amazon River estuaries, the optical water types continuously change from all 3 images show the optical water type continuously change from highly turbid water or extremely turbid water to mandatory turbid water, and then to clear water from the estuary toward the open ocean. And also the particle composition properties are similar. The mineral dominated water are commonly found in the river mouths, and the organic dominated water in the open oceans. And the mixed water regions exist at a transition zone between them. So about the discussion, so combine the 2 water type classification schemes, can our algorithms obtain the high accuracy of SPM estimation? The existing SPM algorithms are limited by relying on a single water type classification scheme, either the optical water type based or particle composition based. Typically, it's supporting the only 3 to 5 water types, but we think the natural water has more complex water properties. So the new algorithm shows the improved accuracy in SPM estimation across the diverse quality environment. The OWT-based algorithm help in wavelength selection, but cannot handle the variation in remote sensing reflectance caused by particle composition different. And the particle composition-based algorithm better compares the optical variability, but make wavelength selection for accurate SPM estimation more difficult. So for the rationale for tracing the appropriate BBP star views, Compared with the previous study of June 21, our algorithm improved the results stem from the selecting the corresponding BBP star value using a particle composition classification method and using the dynamic BBP star instead of the fixed BBP star values. The BBP star values used for organic dominant and mineral dominant water in this study are smaller and largely respectively than those used in June 21, who used the fixed BBP star values to estimate SPM in each optical water type, without considering the difference in particle composition. The fact that the June 21's underestimation of SPM in organic dominant waters, the overestimation of SPM in mineral dominant waters will significantly improve in our study, and it strongly supports that the validate of our proposal. So for the conclusion, the new algorithm includes two water type classification scheme and 12 sub-algorithms corresponding to each water type. The optical water type-based classification scheme helps to estimate the BBP values according to the turbidity of the water body, and the particle composition-based water type classification scheme helps to select an appropriate BBP star according to the proportion of particulate organic matter and the mineral contained in the water bodies. The newly developed SPM estimation algorithm significantly improves its performance and applicability in different water bodies. And the validation using the satellite matchup data also shows a similar accuracy of SPM estimation in SUTA dataset. So in summary, we believe that the new algorithm is suitable for estimating SPM in a wide range of water bodies in worldwide. Compared with the empirical algorithm, our method shows that a better applicability across the water with different optical characteristics. And unlike machine learning models, which often require a large training data set and can be complicated to apply, our algorithm is simpler and supported by the physical optic theory. This makes it possible to more accurately monitor the dynamic changes in the water bodies caused by the human activities and climate change, such as variation in particle size composition and turbidity. And that's all my presentation. Thank you for listening. Oh,
Halo, Mas Fajar.
hello.
I can hear your voice, Mas Fajar.
Can you hear my voice?
Mas Fajar mungkin muted.
Oh, my voice is muted.
No, it's Fajar's microphone. Yours is fine.
Oh, okay, thank you.
Yeah, we are waiting for Fajar's instructions. Thank you.
So
But
if you have questions, you can ask me.
yes, I think Fajar was supposed to provide Q&A sessions. Mas Fajar, we cannot hear you. It's probably audio problems.
Oh, okay. So
Okay.
if everyone have questions, you can ask me.
Yes, we have Miss Dr. Sarif raising his hand, please.
Thank you, Dr. Novi. I'm not doctor yet, actually. Thank you, Mailisu Sang. It's very great presentations. I just curious actually about the classification that you make, the clear, the moderate turbid, the what you call it again, high and extreme, right?
Yeah.
How do you differentiate that class?
Sorry,
I
I
mean,
can't hear your voice.
yeah. Can you hear me?
Hello,
Hello?
sorry, I can't. Yeah, I hear you.
Yeah. Okay. I just curious about the classification, the class that you made, the clear, the moderate, the high, and the extreme turbidity. How did you
Yeah.
differentiate these classes? Is it based on the concentration? Because in some cases, I see that your data you have 2,000 gram per meter cubic, if I'm not mistaken. In Indonesia, that's already mud, not really how do you call it? Not really uh, uh, liquid at that point. It's already mud or something like that. That's why I think in your result you can you share that mostly in the extreme turbid is mineral dominated, not really organic dominated. So I'm just curious in the beginning how you differentiate this class. Is it based on the concentration or is it based on what? Thank you.
I'm not very get you what's your point of your question. So you want to ask about how I divided the remote sensory reflectance
Sorry, Milsi, I think you can go to slide number 9.
Okay. Yes.
Yeah, you have this clear, moderate, high, and extreme.
Yeah.
Before you go to the wavelength, how will you differentiate this one first?
Yes, this is part of 𝐥 21, so I'm not clear to explain it. I can show in the 𥁐 21, he divides the water into the 4 types, and actually it's because in slide 9, he for different turbid waters, they have the different optical water properties. Like in clear water, if we want to estimate if I want to get the BBP values, we need to get the accurate the absorption coefficient. But for estimate absorption coefficient, we need to this slide. And we need to get the absorption coefficient. We need to use the one model called the QAA. But for the QAA, they have one assumption that in 560 nanometers, the water absorption coefficient need to larger than 50% for the total absorption coefficient. But for when the water gets the high turbidity, this assumption cannot be in those high turbid water tests because the non-water absorption gradually to 𝐏𝐭𝐫𝐵 the higher in total supersaturation. So we need to use the more longer wavelengths, like in the highly turbid water type, we use the 754. And for this point, the 𝐥𝐤𝐭21 to use the one systemic dataset to see the those different water water that what the remote sensing reflectance characteristic, and he find yes, this is a clear water types that meet the 560 nanometers. The non-water solution can accomplish the total absorption coefficient about 50%, and this is a mandatory turbid. It used this type must use the 65, and for more high turbid waters, they need to use the 754 or even the 865. So they checked all the remote sensing reflection curves, and he used this one flow chart to divide this different turbid of water types. So we call this type is the optical water type classification.
Okay. Sarif, are you happy with the answer
Yeah, it's
from
very
Mailisu?
clear. Thank you very much.
Okay.
Thank you for your question.
Any other question from the audience? Or we can move to the
I have questions. May I ask questions?
Okay, please.
Yeah, thank you, Dr. Fajar. Thank you, Ms. Mailisu. Very good presentations. I have questions about probably the follow-up questions from previous questions about the water type classification. So I think a long time ago, 𝐥𝐤𝐬𝐿 also classified water into different types. So how's the correlationship or relationships about this classification, your classifications or 𝐥𝐤𝐬 classifications with 𝐥𝐤𝐬's water type classifications? Is it similar or different?
Yeah, you mean the other perverse SPM concentrations, the classification is different with our optical water type classification. So what's the difference between those algorithms with our algorithms?
Yeah. And actually,
Yeah.
a long time ago, there was a pioneer scientist on ocean optics with his famous book, Marine Optics, 𝐥𝐤𝐬, published in 1970 something. And he developed different categories of optical water types. So yeah, so you may want to compare, and I would like to know how those classification are different from yours.
Okay, thank you. Actually, I not know what methods you mentioned, but you can say I compared with the others based on the water type classification. They all use the empirical algorithm. Usually they divided they check the optical water types and to see the what's the difference between those clear water types or highly turbid water, because if you in the the green band, like the January the 17, he used in green band he used some clear waters we can find a correction with the remote sensing reflectance in 560 of the SPM have their strongly corrections, but for the some turbid waters we need to use the more higher reference band. Those they based on the recollaboration data set to find those empirical algorithms. But in our algorithms, we actually is based on the optical theory. like if you know the Li
Yeah,
2002.
yeah.
It's based on the physical serial. So the model is very reliable. And based on our optic water types is based on the QAA, because the QA have the fundamentals that the non-water absorption must occupied mostly by the total absorption coefficient. So we based on this serial to develop the optical water type classification. So the result is very good in June 21.
Thank you.
Thank you,
Thank you.
Pak Novi, and also Mailisu. We have question from Mas Rossi. Are you happy to raise your question by yourself?
Okay, so in the channel?
Or if I will read his question because he sent me a private message. In this research, did you use the Indonesian data? Because I saw in your presentation some data from Asia is still limited in number. You use Indonesian lake data
I
from
will
in your
check
study?
it. So
Maybe
this
not
is
yet.
graph of maybe so
Okay.
Indonesia, maybe not.
Okay, maybe later we can cooperate to apply your model to, because in Indonesia there is several different type of water. So maybe we can test your model and try to estimate the SPM, right?
Yes,
Okay, I need one more question. If no, we can move to Pak Adi, Pak Novi to present. Okay, so from Pak Sarif, Dalin Jiang actually used Indonesian data from Mahakam. Maybe we can also check his publication. Okay, thank you once again, Mailisu. If you are okay, you can stay here and wait for another discussion because we will have a second round. So next is my pleasure to introduce the second speaker is, wait. I will read the short CV from Dr. Novi Susetyo Adi. He obtained his PhD at the University of Queensland, Australia, with the concentration of seagrass ecosystem productivity mapping and spatial modeling in 2014. His experience is from 2005 until 2021 in Ministry of Marine Affairs and Fishery as a researcher and senior mapping surveyor for 3 years from 2022 until 2025. And from 2025 until now, he became the head of the Center for Socio-Economic Research on Marine and Fishery. His main project is one is research for title 𝐭RMAP CTI 2021 until 2022. SATREP, I believe this is from the Japan government foundation. Asia Joint Research Program, 𝐿ASIA-GRP, Asia Pacific Network for Global Chain Research, APN, Science, Technology, and Action Nexus for Development, or STAN program, Indonesian Seagrass Partnership 2022 until 2025. And today uh, he will present the title Ocean Color from Science to Application to Support Decision Making in Marine and Coastal Environment Management. So, Pak Novi Adi Susetyo, Pak Novi Susetyo Adi, the screen is yours, and we will follow with question and answer. While the Pak Novi present his research or his stuff, the participant can also write their question in the chat box, and we will consider in the question and answer session. So, Pak Novi Susetyo Adi, the screen is yours.
Thank you, Pak Fajar.
Okay.
Can you hear my voice?
Yes, clearly.
Okay, thank you. Thank you very much. Very good morning, everyone from Jakarta, Indonesia. First of all, I would like to thank Research Center for Limnology and Water Resource, BRIN, Indonesian National Innovation and Research Agency, for hosting this interesting seminar, this important seminar as well. And actually, this seminar started from a small community. My colleagues who have been working on this ocean color for a while, and through time, actually, we changed our affiliations, we changed our positions, but what united us was that we still have a common interest in ocean colors. So then we decided to organize this seminar. So hopefully we could share about the science part, which was already presented by Ms. Mailisu, and then probably the applications part, which was assigned to my part. Okay, thank you. This is the applications part that I was assigned for. And probably for the first 3 or 4 slides, I would like to repeat or probably reiterate to emphasize like the general scientific background of ocean color before moving to the applications parts. So this is actually the signal, electromagnetic signals coming from the sun. The sun is in this picture is in the upper left positions, and then there are rays of electromagnetic from the suns coming to the oceans, and some are reflected on the ocean part, on the ocean surface. Some are going into the bottom of the oceans, for example, for the shallow water environment. And then from these interactions with in water substance or the bottom of the shallow water, then the reflected radiations coming up to the surface oceans and captured by the satellites. So for the ocean color, actually, we want to capture a signal from the surface of these oceans. So this is basically the ocean satellite color imageries that we received today. And yes, this is actually the water living radiance that we are interested in to obtain some ocean properties, yeah, in water constituents. And yeah, as mentioned also by the first speaker, we have different type of waters optically. So this is like the optical classification of water. Generally, we have 2 big types, yeah, 2 general types. Case 1 waters, which is the oceanic waters, mainly consists of phytoplanktons. It's like open ocean water. And then we have case 2 waters. So this is typical of coastal waters. And yeah, as I also asked the first presenter, actually, previous researchers had already divided this case to water into subcategories, yeah, like very turbid, moderate turbid, and etc. So basically, this is the how the ocean color remote sensing works, and the optical classifications of waters. And actually, this ocean color remote sensing is scientifically, it is rooted from oceanography science itself. So we may be familiar with physical oceanography, biological oceanography, chemical oceanography, but in Indonesia, probably we rarely study or hear another branch of oceanography, which is optical oceanography. Yeah, so this is very physics, very physics oriented object, but actually the ocean color remote sensing is rooted in the optical oceanography. So yeah, the branch of like the application fields of optical oceanography consists of ocean color remote sensing and also shallow water remote sensing. I will touch a little bit for the two of them. Okay, and then yeah, as mentioned by also Miss Mailisu, the first speaker, she's using one of the basic methods for deriving ocean color parameters like chlorophyll, turbidity, surface temperature, etc. So basically, there are three main types of the methods. Yeah, the empirical methods, the semi-empirical method, and then the analytical method. So some scientists categorize differently for these methods, and one of them, the additional method will be the semi-analytical methods. Yeah, so yeah, this is just to give like general methods in ocean color. Okay. Yeah, probably briefly, empirical method means that in situ ocean color parameters like temperatures, chlorophyll, turbidity, etc., are directly correlated with remote sensing bands. Yeah, without knowing the underlying inherent correlations between in situ water constituent parameters and the bands used. So basically just like a random correlations, and then we get a high R square value and then we use it. Yeah, that's the like the rough method. Yeah. So ocean color scientists are normally avoiding this method, because this is very simple, very simple assumptions required. And then for the semi-empirical and analytical and semi-analytical, actually it is developed from in situ measurement, using radiometer, using spectral radiant measurement in the fields. And then some correlations are made between the water constituent, chlorophyll, turbidity, etc., and the radiance from in situ measurement. Yeah, and then after those correlations are established, then the resulted algorithm could be applied to remote sensing. So basically, that's the basic methods. And now I will start talking about the applications aspects. So why we need operational ocean color system? So I like to use this terminology, operational ocean color system, because it means transitions from ocean color science to operational ocean color application. Yeah, so it's transformed from science to operational applications. Yeah, and here I use two examples, coral bleaching and harmful algal bloom, just to emphasize why we need this operational ocean color system. And those bleaching and harmful algal bloom comes from environmental degradations. Yeah, it's like a results of environmental degradation, or two examples of environmental degradations that comes from direct human impacts, direct human activities, and climate change. Yeah. So bleaching could result from pollutions, high turbidity, and bleaching could result also from like the pressures on the coral reefs due, for example, unsustainable marine tourism, for example. And bleaching could also come from the increasing temperatures of ocean surface. And so those causes both direct human impacts and climate change impacts coral reefs. Okay. And then similar things also applies to harmful algal bloom. If we have excessive nutrients coming from human activities, then toxic algal blooms may occur. And massive death of fish could take place. And also the impact is ecology and also social economy. If commercial fishes die off massively, then it will impact the fishery sector, for example. And for example, if coral reefs are impacted, coral reefs are bleaching, and then leading to massive death, then of course marine tourism sector is also impacted. That's why we need, like as I mentioned earlier, operational ocean color, like integrated permanent ocean color monitoring system, for example. I will touch that later. This is just like an additional slide on the impacts of human activities and also climate change. We have pollutions, we have overfishing, etc. And some impacts may be monitored by ocean color remote sensing system. For example, like pollution, coral bleaching, through the increasing sea surface temperature, and then increasing turbidity. We could monitor them using remote sensing of ocean color. And then it comes to the Indonesian context. We have Indonesian is the largest archipelagic states in the world. We have more than 17,500 islands scattered from from west to east. We have many islands. That's why we are called as the largest archipelagic states. And then we have also many marine protected areas. We also have the marine special planning regulation or policy. And we have direct human impacts in the form of, for example, pollutions, increasing turbidity, etc. We have also impacts of climate change in the form of more frequent coral bleaching events, for example, and those combined impacts, for example, combined impacts of increasing sea surface temperatures and direct human pollutions may also trigger more frequent toxic harmful algal bloom. But unfortunately, we don't have yet operational ocean color for monitoring, for example, Indonesian MPAs. We don't have yet like the operational ocean color monitoring for marine pollutions. Including in that marine pollution are increasing turbidity, and then increasing toxic harmful algae bloom, yeah, increasing water nutrient, etc. We don't have yet that in place operationally. Yeah. So this picture actually depicts the some Indonesian MPAs. Yeah, Indonesia has targets for increasing its MPA in the 2045, consisting 30% of its ocean territory. So we are now still targeting 10% of MPA in 2030, and then we have ambitions to increase MPA to 30% of our ocean territory. Yeah. And then we have this, we have these various marine spatial zones. Yeah. If you can see here, our countries is crowded. Yeah, is crowded by different type of marine spatial zone. Yeah, we have zones of cross-cutting region. We have spatial zone at provincial level. We have what we call as the national strategic zones, and we have zones for our outermost islands. We also have zones for our MPAs, as I mentioned earlier. But yeah, as for the context of this webinar, we don't have yet, yeah, ocean color parameters integrated monitoring system in place. Yeah, and then yeah, it comes to the several applications. So we have like direct applications of remote sensing, including ocean color remote sensing. For example, for the direct aspect, we could use remote sensing, ocean color or optical sensors, for example, for mapping geomorphological features, and then habitat complexity, and then underwater habitat, and etc. And then for those, for example, coral ecosystem, we also could extract remote sensing using ocean color for our indirect parameters. I mean, not directly for the, for example, coral reef object, seagrass object, or mangrove object, but the surrounding environment of those ecosystem. For example, the surrounding sea surface temperature, surrounding turbidity, surrounding chlorophyll, etc. Yeah. And then, yeah, this is specifically parameters that can be extracted from ocean color remote sensing, mostly water quality parameter, or another terminology is in-water constituents. We could extract color dissolved organic matter, CDOM, sea surface temperature, chlorophyll, yeah, total suspended matter, which is the focus of Ms. Mailisu's research work, and then some light parameter, for example, and euphoric depth, for example, the depth where the sun rays could still reach water column. Yeah, for the shallow water remote sensing, yeah, we have ocean color remote sensing, we have shallow water remote sensing. Yeah, we could map bottom habitat, yeah, and then ocean color itself could be used to extract water optical properties, yeah, chlorophyll, turbidity, sea surface temperature, etc., and also bathymetry, yeah, satellite-based bathymetry. And the application, as I mentioned earlier, it will be useful to monitor the water quality of MPAs, and also, for example, to design MPA itself, because MPA has several zones. For example, the core zone or no-take zone, buffer zone, and etc. We could use the parameters from ocean colors to design MPAs, and yeah, etc. And then coming back to the coral bleaching and harmful algal bloom in Indonesia, actually, to some extent, we have records of coral bleaching taking place in several years. Yeah, and scientists mentions that coral bleaching now becomes more frequent because of the warming oceans, yeah, due to climate change. And actually, in Indonesia, also occur harmful algal bloom actually, but it's not uh, well recorded, yeah, as the coral bleaching events. Yeah, so we may have in the past we may have read news that there were massive deaths of fish in Bay of Jakarta, for example, and for example in other lakes, yeah, used for aquaculture activities. So yeah, those were the harmful algal bloom events, but we rarely studied these events compared to coral bleaching, for example. And yeah, coral bleaching alert system for Indonesia is very important. Yeah, because we are the largest archipelago states. Yeah, and we have many MPAs, and many MPAs protects pristine coral reefs. Yeah, and coral reefs are prone to increasing sea surface temperature. Yeah, and so sea surface temperature can be extracted from ocean color system or satellite. Yeah, that's why yeah, we need actually we need coral bleaching and harmful algal bloom alerts actually, or integrated system of those. Yeah, actually, this globally, this bleaching alert system based on satellite data already exists. Yeah, developed by NOAA, and the U.S. Aerospace Agency. Yeah, actually, it's based on the climatology sea surface temperature system. Yeah, so yeah, actually it is very technical. We may need special sessions to discuss about this system. But basically, they have like time series sea surface temperature imageries, and then they calculated like the base, yeah, the base temperature, yeah, the base temperature that can be compared with, yeah, and then based on those time series analysis, they compare uh, uh, the result of the sea surface temperature analysis temporarily with that basic temperature. Yeah, I mean, if deviates from that basic temperatures higher, then it will be breaching even, or if it's under, then it will be like a cooling events, something like that. And yeah, this is some relevant satellite missions and water quality extraction. We have several satellites and in our space. But yeah, those Terra, Aqua, and then Sentinel-3 are categorized as ocean color satellites. I will go quickly on this. And yeah, this is Terra, Aqua, Sentinel-3, ocean color. They are ocean color satellites, and they are free. Yeah. And then this is like the extractions of some ocean color parameters, chlorophyll, using CWIF satellites, 9 kilometers spatial resolutions, mainly for case one waters. So CWIFs, yeah, it was launched in 1997 and until 2003. And this is also chlorophyll, yeah, from the shortwave infrared algorithm for the Chesapeake Bay, United States. And also this is from the chlorophyll from the China East Coast. Okay. And yeah, this is another improvement, yeah. So ocean color remote sensing is very improving fields one of the very improved fields. So new algorithm have been developed, new satellites have been launched. Yeah, and then this is the one parameter, one important parameter. Another indicator of water clarity, diffuse attenuation coefficients. Yeah. And this is the product of color remote sensing. And there are some challenges actually. For example, ocean color satellites mostly comes in a coarse spatial resolutions, about 1 kilometer. But our, for example, pollution case may take place in 200 meters resolutions, for example, or more detailed resolutions. That's the limitations. And then coastal ocean events or phenomena happens at very short temporal scales. It's different from like geological scales that happens in like 100 or 1,000 years. Ocean color phenomena happens in a matter of seconds, minutes, hours. So if the temporal resolution of the ocean color satellites don't match those time scales, then we could not capture those events. And then I think it's part of the Miss Mailisu's research. We have limited spectral resolutions. Coastal waters are very complex. High turbidity, mid turbidity, low turbidity, etc. And the water constituents comes from various sources, from land-based sources, from ocean-based sources. It's very complex. So we need actually more detailed spectral resolutions to extract water constituents from coastal waters or from case 2 waters. This is an example of how spatial resolution impacts, for example, our ocean color parameters. This is the left-hand side picture is spheres, and then the right-hand side is Landsat, the newest Landsat sensor. The right-hand side picture has 30 resolution spatial 30 meters resolution, and then the left-hand side is at like 700 meters resolution. So if we want to focus or to study spatial resolution at more detailed resolution, then we need more detailed spatial resolutions. And then we still need more understanding on the spectral pattern of objects, different objects, or difference, for example, in water constituents. And that's we can achieve only from, for example, in situ measurement. And then this is, for example, the difference reflectance of turbidity of different concentrations, for example. We need more understanding on the basic spectral pattern of this in water constituent substances. And then environmental complexity is stronger impact. It has stronger impacts on satellite imageries than sensor quality actually. So we may have very sophisticated sensors recently, but from this research, from this paper, actually the environmental complexity factors are more influential for the good quality extractions of oceanographic remote sensing. And then this is noise and accuracy. The noise signal is higher. Is much higher actually than the signal of the object themselves. That's why we will need very rigid atmospheric corrections, in general noise corrections to really isolate the object that we want to extract from the ocean color remote sensing. So this is a challenge actually. And I'm coming to the end part of my presentations. So we could also combine satellite remote sensing parameters with couple ecosystem or climate model for various purposes for managing our coastal and ocean environment. Yeah, basically we have models and we have parameters for model inputs, and some inputs can be extracted from ocean color remote sensing. Yeah, basically in general, that's the how integrations of ocean color remote sensing and models works. Okay. And actually, to some extent, ocean color scientists, including Indonesian scientists, have worked in this part. So we use not only satellite imageries, but we use also buoys, we use also in situ sensors, and to some extent in the past, we already integrated it. Yeah, but those were still in like a scientific or experimental stage. Okay, but we need those components of works to create integrated operational ocean color for Indonesia. Yeah, so I'm sorry, I apologize. These boxes might not be very clear, but basically here, actually, I already proposed some years ago that we need like this kind of Indonesian operational ocean color system consisting of different sub system. Yeah, for example, bleaching alert system, and then turbidity alert system, harmful alga bloom alert system, etc. And then those sub-components are integrated into sustainable Indonesian ocean color Indonesian operational ocean color, combined with the measurements from models, measurements from in situ sensor, measurement from in situ buoys. Yeah, actually, this is like an ideal system. Yeah, and personally, as an Indonesian person working in Indonesia, we may need our Indonesian Aerospace Agency to develop and host such system that can serve different ministries. Yeah, for example, Ministry of Marine Affairs and Fisheries, where I'm working at. Yeah, to monitor its MPAs, to monitor the impacts of aquaculture ponds, for example. Yeah, to monitor the impacts of different regimes of special planning allocations, etc. But it is like centered in one institutions, and then served to all ministry and to all applications. Yeah, yeah, that's the what I have in mind. Like what US NOAA's works. Yeah, they develop this algorithm. They work in situ using in situ spectral measurement. They develop algorithm, and then they apply those works, those scientific works, in like, for example, NOAA bleaching alerts. Yeah, yeah, bleaching alert is like a operational tool. Yeah, we could use that, but yeah, it is still at global level. We may still need like Indonesian versions of bleaching alert, chloro bleaching alert. Yeah, I think that's the main part of my presentations, but I have like several additional slides for in situ equipments to support ocean color remote sensing works or research. And to some extent, I already worked in the past with these equipments. Yeah, this is, for example, for measuring the apparent optical properties. Yeah, this is for measuring the inherent optical properties. Yeah, and then, yeah, this is the setting of the apparent optical properties. 3 sensors. Yeah, one sensor measuring the water, one sensor measuring the irradiance, yeah, upward positions, and then one sensor slightly measuring the sky radiance, yeah, for example. And then, yeah, this is the setting the field. This is what we did in the past, myself on the boat long time ago. Yeah, this is the setting. We conducted this kind of works in the several Indonesian waters in the past. This is the complex settings in the boat. Yeah, and this is actually the PER sensor, like the light sensor, photosynthetically active radiation sensor. Yeah, this is the photosynthetically active radiation sensors, like the 3D and 2D sensors, measuring upward radiance and downward radiance as well. And then, yeah, we also use additional sensors, yeah, for example, for validation. This is the profile water quality, measuring chlorophyll, turbidity, sea surface temperature, etc. at depth profile, not just at surface. And then we use this water pressure logger, and then, yeah, we use this chlorophyll and turbidity logger simultaneously with optical sensors that I mentioned earlier. Yeah, and we use this like the depth sonder. Yeah, that will be all. Thank you very much for your attention. Thank you.
Thank you, Pak Novi, for your insightful presentation. And we have plenty time for discussion. We have one question from Dino Gonzalez. Dear Dr. Novi, can ocean color analysis be used to predict coral bleaching and algae bloom by looking at its connection with climate change? And is it possible to apply this method in inland waters such as lake? From Dino Gonzalez. And the second question is, this is the operational question, I think. Could we request to borrow the equipment for survey? From Pak Sarif. Dr. Novi, can you address the question from Dino Gonzalez related with the algae bloom and coral bleaching and connection with climate change?
Yeah, thank you, Mas Fajar. Thank you, Mas Dino. This is a good friend of mine, actually. We used to work in one institution before we took our own different ways. Yeah, thank you. Yeah, we don't have corals in lakes. Yeah. So yeah, the application of ocean color satellites for bleaching in lakes is not relevant because we don't have coral in lakes. But yeah, we have like harmful algal bloom or excessive turbidity events in the lakes. Yeah. So we have several lakes used for example, shrimp or fish pond fishing. Yeah. And sometimes because of the excessive feeding, and then we have different like the wind patterns, then the feeding deposited in the bottom of the lakes stir up in the surface. Yeah, and it creates a toxic environment, causing massive death of the fish or shrimp. Yeah, those are events or phenomenon that normally happens in the lakes. And for that events, it is possible we use this ocean color remote sensing, of course. Yeah, for example, from the chlorophyll increasing concentrations, or from the turbidity increasing concentration due to the stir up of the feed, fish or shrimp feeds that deposited in the bottom of the lakes. Yeah, when it's stir up in the surface, then it will be visible from ocean color remote sensing. Yeah, but of course, again, as I mentioned earlier, the size of the lake or the size of the impacted area should match the spatial resolutions of the ocean color satellite. Yeah, for example, if the event or phenomenon or the phenomena happens in 10 meters spatial resolutions, then of course we cannot detect those events using for example 1 kilometer of ocean color satellite imageries. So it's very possible, yeah, for monitoring lakes, yeah, inland lakes using ocean color remote sensing. But yeah, again we need what I would like to emphasize with my presentation, that we need operational ocean color system, not just for example, downloading or processing one imagery for random events, but operational. Thank you. I hope it answers.
Thank you, Dr. Novi. The key word is we should consider the spatial and also spectral resolution for the operational ocean color system. We have Bu Wiwin Ambarbulan. You raise hand.
Yes, Pak Fajar.
You have question for Dr. Novi
Yeah.
or Miss Mailisu?
Actually, for both of them.
Oh, okay.
Okay,
Please.
thank you. Yes, thank you very much for Dr. Fajar. Thank you for Miss Mailisu. I'm sorry if I pronounce your name not proper. And also for Dr. Novi, your presentation is really very nice and very important in state of the ocean color mapping. So I missed the part of Miss Mailu presentation. And the first question to her is about, if I'm not mistaken, is you measure about total suspended mapping by combining optical water type and quasi-analytical approach. So this means every water type, you have different 𝐏𝐸 implementation based on the peak of the wavelength, something like that. So that means we want to apply the OAT type. So that means we have to measure the apparent optical property in situ. In the case we don't have the in situ measurement of the AOP, can we still implement the optical water type classification? If there's still, can we use, what kind of the parameter can we using for differentiate the optical water type? And the second, can we use the remote sensing reflectant, the water reflectant remote sensing from the satellite? So I mean, not from the in situ measurement, but from the deriving from the satellite data. We can use this for the qualification of the water type. And the second question, I would like to know about what kind of the atmospheric correction did you implement in mainly in your study? Maybe you can give me a suggestion for the tropical water, like Indonesia. What are the most robust but simple atmospheric correction we can apply? And the third one, the final one, I would like to ask about the validation. The validation of the remote sensing result, we should be using the in situ observation. But in case we don't have the in situ measurement of the inherent optical property like TSM, CDOM, or chlorophyll A, so can we use the global satellite data such as the global color to use for the validation? So that's all my question to Miss Mailisu. It's clear, maybe my English not proper. And the second, I would like to ask to Dr. Novi. In the last presentation, you show us about the instrument you use for the apparent optical property. Actually, I would like to have to propose a proposal to doing the research in the ocean color remote sensing in Indonesia, but I still smart question where we can find the instrument for implementation this work, because I still working with the bio-optical modeling like your expertise, so we can join together maybe in this, but we need the instrument. So in which institution we can find this instrument? So that's my question, Pak Fajar. Thank you very much.
Okay, thank you, Bu Wiwin Ambar Bulan. So, Mailisu Sang, are you still here?
Yes, but
Yeah.
I'm sorry I missed some question of her. So there
Okay.
are 3 questions.
Yeah, I will
Yes.
try to okay, with Ambar Bulan, can you repeat, or I will explain to
Yeah.
Mailisu? Yeah.
Okay. Miss Miu, when you applying the optical water type, you're using the in situ observation of the inherent optical property, apparent optical property like a remote sensing reflector, isn't it? So you measure the reflectance of the water, the atmosphere, something like that, using the instrument?
You mean the in situ data set, what we used?
Yeah.
Yeah, we used a data set called the Gloria data set. It's published, everyone can use it. It's published in online.
Okay. So this means you are not measure on in situ observation, yeah, for the apparent optical properties. No, using the that.
It's all about it's according to field service to get the in situ reflectance.
Yeah. Okay. My question is this possible to do the optical water type classification without the in situ measurement of the apparent optical properties?
You mean if we can use this optical water type classification in miss some of them?
Yeah, for example, I didn't go to the field. I didn't measure the apparent optical property, but I want to do the research using your work.
Recording in progress.
Using the optical water type classification. Is still possible to do this one?
Can you repeat your question? Sorry.
Okay, maybe not clear. Yeah. Okay. Maybe I will. Yeah. Maybe we
Maybe
can ask.
Bu Wiwin can write, so the
Yeah.
question will be clear, and then I will
Yes.
follow up later
Yeah.
for the answer.
Okay.
Yeah,
Thank
So
you.
yeah.
for the
Yeah.
confirmation, Mailisu Sang used the Gloria dataset. It's data available from around the globe. So there is
Okay.
a pair dataset of water quality and also the inherent optical properties. So he take several data from around the globe with different or various types. So he developed
Okay.
classification first and then combine with the
Yeah.
QAA and use the different suspended particle matter algorithm
Okay.
also. Mm.
Okay. So this means without using in situ observation, yeah, Pak Fajar, yeah, using all the available in situ data from the available in the internet. Okay.
Yeah, it's in the data portal is Gloria.
Oh, Gloria. Okay. So
Yeah.
how about the validation? He also doing the validation for the result.
How Mailisu Sang, you got the question? How you perform your validation?
I compare validation is use the Gloria dataset and use the real satellite images. And we compare the other 11 SPM algorithms.
So in the presentation, Mailisu separate those Gloria dataset into calibration and also validation, and then later they use the satellite data set paired with the water quality data. So after building the model, so he applied the model for the real satellite with pair with in situ water quality. So he can, yeah, yeah.
Also, that's mean Miss Mailu research all based on the satellite data from the product data or with the raw data, satellite data. Yeah, Pak Fajar. Yeah, okay.
Okay, Bu. Yeah.
But how can
And
make sure
last one,
our
the atmospheric
yeah.
correction, Mailisu, you perform atmospheric correction for your satellite
Yeah.
image? Yeah.
I used atmosphere correction. It named the C2RCC and is suitable for inland waters, especially.
Yeah, you use C2RCC, yeah.
Yeah, C2RCC.
Okay, because the atmospheric correction is the main part of the working with the ocean color data, yeah, Miss Mailu, so this is really important. Okay, thank you very much for the question, and thank you, Pak Fajar, for clearing my question and the answer.
Okay, thank you, Bu Wiwin.
And Pak Novi,
Pak
the
Novi,
instrument. The
you
instrument.
still have one question from Bu Wiwin
Yes,
regarding the proposal and also the
yeah.
cooperation for the measurement using your instrument.
Yes, yes. I hope I already changed to mobile phone, so I hope you can still hear my voice. Yeah.
Yeah, yeah, it's still clear. Thank you.
Thank you. Yes, probably also to answer Dr. Sarif as well. Thank you for the questions, Dr. Sarif and Ibu Dr. Wiwin. Yeah, what I already show in my last slides, actually it was meant as a complementary slides. Actually, the works that I did in the past, when I was still affiliated with a research unit under under my ministry. Yeah, and then as we may be familiar about the development or about the conditions, then our research units disbanded. Yeah. So yeah, actually those equipments are still in my labs. Yeah, but those labs and how to say, that lab is not active anymore. Yeah, and it's not well maintained anymore. Those equipments are still there. So probably after this seminar at later time, we could talk again, or we could discuss again, and I will ask about the current condition of that lab. Yeah, we have very sophisticated sensors, like the radiometer sensors, and then those loggers. Yeah, and then we put it in the fields simultaneously with the optical inside the measurements, so then we could match like ocean color parameters from the optical measurement and from the logger measurements of chlorophyll and turbidity, etc. Yeah, actually. But unfortunately, those equipments and the lab where they are host actually is not active any longer. Yeah, due to the organizational change. Yeah, actually that organizational change actually changed the way we work a lot actually. But yeah, probably after this seminar or at later meetings, we could still discuss about it, and probably probably small additions from Bu Wiwin questions to Miss Mailisu. Yeah, if we don't have inherent optical properties parameters measure from the in situ SA9, for example, or similar sensors to measure IOP, yeah, we could still try to use the IOP measurement from lab measurement book. Bu Wiwin. Yeah, we could sample the water, and then we could still try to measure the inherent optical properties from lab measurements. Yeah, I think. Yeah, but I don't know yet if the lab equipments for those available. But basically, it's like spectrometer equipped with some like integrating spare, something like that.
Yes, yes.
Yeah, that's still possible. But probably we need to try to begin to look at our laboratory equipments. Yeah,
Yeah,
and then
yeah.
another option is to use the Lee algorithm. Extracting inherent optical properties from the semi-analytical algorithm from ocean color. Yeah, what we could do is just to try and to play with those possibilities. Yeah, I hope it answers. Thank you.
Okay, thank you, Dr. Novi.
Thank you.
Yeah,
Thank
to
you,
measure
Pak
the
Novi. Yeah.
IOP, we can use the spectro, and with one more additional equipment is integral sphere. So, but I still cannot find this integral sphere in our laboratory in Indonesia. Actually, this just an additional, so it can measure the IOP from the filtered water. So but this is should be set by special equipment for the, I think, Shimizu UV visible. So, but this additional equipment is maybe rarely in general application, but it's important in ocean color study. So, any other question from the participants? If no, because we already reached the end of time. So thank you for Miss Mailisu and Pak Novi Susetyo Adi for your insightful presentation, and thank you to all participants for joining today. We have more than 70 participants join us today and stayed until the end. I hope today's webinar has provided valuable knowledge and inspiration for your work in water and environmental management. A special thanks to Dr. Luki Subehi and our supporting organization, the Research Center for Limnology and Water Resources, BRIN, the Indonesian Society for Limnology-MLI, and the Indonesia Ocean Color community. So before we end up our webinar, I ask all participants to open their camera for the photo documentation. So Mas Aldiano will take several screenshots for documentation. Please open your camera, and Mas Deo, are you ready to capture the screen?
Yeah, Mas Fajar. In my screen, I have 2 layers. So I will
Okay,
count for the first layer.
give your perfect smile.
Okay, 1, 2, 3. Next layer. Wait. Okay, 1, 2, 3. Okay.
Okay, once again, thank you for your time and participation. If you want to communicate more with the presenters today or for each participant, you can contact me and I will share their contact for Mailisu and also for Dr. Novi. So thank you for your time and participation. Wishing you all productive day ahead. Wassalamualaikum warahmatullahi wabarakatuh.